My name is Lionel Reveret. I'm a researcher at INRIA. INRIA is a public research institute for computer science. And I'm myself expert and I'm myself interested in motion analysis. Today I will present you our work with my colleagues, Sylvain Chapelle from FFMI, Frank Kane from Université Grenoble, and Pierre from Université of Lyon about 3D motion analysis of speed climbing performance. So what we are interested in is to bring insight biomechanical analysis to help to improve performance in speed climbing. So here you see the performance run by Anouk Jobert at the Pôle France in Guaron on the speed climbing wall. So we are first particularly interested in kinematics analysis, so to get the motion, the motion 3D. So in biomechanics, when you think about kinematics analysis, so traditional approach is to use marker-based systems. So you've seen some example of that. So you put markers on your body. So we have a studio like that in Grenoble at INRIA. We have a motion capture facility with 68 video cameras and 24 mocap cameras. But this kind of system is absolutely not adapted for climbing because the exploration of volume is limited by the fixed position of the cameras. You have to maintain a controlled lighting, and you have to perform a manual calibration procedure. So definitely not adapted for speed climbing performance. So Frank mentioned this project. So we have a project with Frank, Pierre, and Sylvain, projects funded by the Région Rhône-Alpes near Grenoble, to do a 3D analysis from video. So that's the main idea of the project. So the FCAP project, to do motion capture for kinematics and biomechanical analysis from video, with the idea of taking the video as an input and provide this output for 3D analysis. So when you do 3D analysis, so the key idea of doing 3D analysis and the key constraint is to have multiple point of view. So if you have only one point of view, you cannot do 3D. So if you want to do 3D analysis, you need at least 2 points of view. So you need two synchronized view at least, and then you reconstruct 3D with stereoscopy and triangulation algorithm. So like you have 2 eyes that allows you to see in 3D. So if you have only one eye, you don't see 3D. So we have the same constraint here, and so we will work. So in order to recover 3D information, in order to do 3D motion analysis, you need at least 2 points of view. So this is what we are doing. So if you use so you will hear live capture at the So this video has been taken from an iPad, and this is a device that actually most of people are using and they're convenient. And when you take standard video from the ground, so you have a problem because you tend, as you see on the video, have strong visual distortion at the top. So how the subject is going farther, so it gets smaller and smaller, and the camera tilts a lot, and so you are not facing you are not facing anymore the subject, and so you have this distortion. And this distortion because of change of point of view, the tilting of the camera at the end, alter and introduce limitation on image processing possibilities. So the idea of the project, one of the key ideas of the project is to use drones. And so if you use 2 drones, because we want to do 3D analysis, so you maintain the point of view that is right facing the subject and with no distortion. So in the next video, here you can see the result with 2 synchronized video taken from the drone. And so you see that from the ground to the top, you get clean and undistorted image, and so you can perform interesting and more convenient image processing. So what you see here is our first goal, so first step in the project which is to recover the 3D trajectory of a marker attached to the harness. So the first step you have to do is to do online calibration of the cameras. So you have to know what is the respective position of the two drones, which one with respect to each one. When you do traditional motion capture, you don't have this kind of problem because the cameras are fixed. So you do the calibration, and then your calibration is good for the day, and you don't have to come back to the calibration procedure. Here, you have to look at the drones are moving, and you don't know the relative motion of the two drones together. You have to calibrate at each frame, And so this is what is shown here. And so through a 3D reconstruction of the wall, you can recover exact calibration and the position of the drone. And so that's the first step for the algorithm. And so also, how do we want to get the 3D trajectory of the marker? So what we do is to track in 2D for each view the position of the markers, and then through triangulation algorithm, so stereoscopic construction, you can generate 3D position of the markers in a world-based coordinate. So now you have information about the climber, not related to the camera, because the camera is moving, but related to a world-fixed coordinate. So you can start to do some interesting biomechanics and kinematics analysis from that. So here you see 3 different views with a stabilized world. So one way to interpret that is to think of this processing as a filtering of the motion of the drone. So we are filtering out the motion of the drone, which is not related to the motion of the climber, but so this motion is related, and so we are now in a fixed wall reference frame, and the position of the markers on the harness is recorded in 3D. So just as an illustration of this ability to generate new views, and so here I generate the virtual view above the 3D markers of the harness, and apply back this virtual view in my stabilized work environment. So if you go to some quantitative analysis of what we recorded. So here you got the XYZ coordinate system for the markers. So up, so green is 1, so it's going up. Red is lateral motion, and blue is out of plane motion. And so you can see that along the trajectory, so you can record XYZ trajectory during speed climbing performance. So obviously you got this Y, which is steep L, which is a regular progression of Y, and you get this on Z, you get this inclined, and you get this slope. And actually these slopes come from the fact that the wall is tilted 5 degrees. So the speed climbing the wall is tilted 5 degrees, and this is as you're walking in 3D, so you can you can change the reference frame, and so you can go back to the reference frame on the wall, and you can filter out this artifact, and then here you get a Z, which is expressed in the reference wall, in the reference frame of the wall, and so you get a way to assess the position of the climber with respect to the wall, so how far it goes from the wall. So once you get the trajectory, and so we are talking about speed, so it's interesting to see speed, and so what is the speed profile of the climber? And so what I've shown here is speed on each one of each component, X, Y, Z component, so the B component. So this is the speed in X, so how fast it's moving in the X direction, and so for the Y, and so for the Z. And so I also represent the norm of the speed. So the norm, I just recall quickly, the norm of the speed is the amplitude, the maximum, the total amplitude of the speed. And so the idea is to examine that, to investigate, to examine actually what is the most important is the loss of vertical speed, because this is what dictates the chrono, it's what dictates the performance. And so now that we have these quantities, I display here the ratio of the X, Y, and Z speed with respect to the total speed. And so with the idea that we want these to be close as one as possible, meaning that the amount of speed that is used by the climber is totally devoted for going up. So any other speed leak here is a potential loss of performance. And so if you compare that all together, so if you put everything all together, so these are normalized quantities, so the ratio of x over v and y over v in terms of speed, so you can start to see interesting profile of the performance along the rail. So here you get also the trajectory of the center of the markers along the reference of the holes, and just to get an idea of where is the climber during the ascension. And so here you can start to see that you have some moment where the y direction is not dominant. And so here you get the z velocity, so the out of plane velocity is getting higher than the y velocity. And so you get also some moment where the lateral velocity is also getting higher. So of course, most of the motion is going upward, which is a good thing. But sometimes, so you see that sometimes the y is not the most important, or actually you get some loss of y. And so talking with the coach about that, so it allows you to identify some key moments during the progression where there is potential for improvement of the upspeed performance, because here you got a loss of this y component of the speed here, and here. And so this is an example of how you can work with advanced technical tools to help and try to collaborate with coach to get some hints to improve the performance. So just to wrap up this first result, so we have a potential for 3D kinematics analysis. So this is okay for analysis of velocity, but if we are talking about dynamics, we may ask ourselves that is the point of the harness the true center of mass? So obviously, so you get the intuition that the center of mass is not on your back. The center of mass is kind of shifted toward the center of your body. And so this is what we have been interested in here in this study, to assess how different are the points on the harness compared to the true center of mass, with the idea that this study will go to biomechanics and not only kinematics. So we use a facility at the lab where we have 68 cameras, and so from these cameras you can do a 3D reconstruction of the body in motion. And so here you got a 3D mesh, the animated 3D mesh for the climbers, and this is overlaid on the subject. So to partially answer one of the questions, so we are doing this with 68 camera, because if you use a depth camera is just facing you and it gives some very crude results. And so here it's much the level of detail is much higher with this kind of facility. And so now you can see that so in white you got the markers in the harness, so and so in green you got the estimation of the center of mass. So as you got a 3D mesh for the subject, and so with an hypothesis of homogeneous density, which is quite right for the human body, so some literature about that. So you can compute mathematically the center of mass, the true center of mass. And so you can see that the 3D mesh reveals that the true center of mass is shifted here, and also it reveals that you can measure the center of mass using this 3D mesh. And so it confirms us in pursuing this research using 3D mesh. So now we have the last part of the talk. So we've seen that we manage with the drones to capture interesting 3D information of one point on the harness. But this is not enough. So we are interested in the full body approach. And so the mesh show that you can have some interesting dynamics using 3D mesh. Going from video to 3D mesh, we've seen in the lab that we can make it with 68 cameras. But in real world, in the situation, we got only 2 drones. So we cannot achieve the same quality with 2 drones. So it would be difficult. So as I said, having 2 drones is enough to get 3D position of 1 markers. But for a full body solution for real world, so when we're going to work that is to reuse the 3D model that has been learned in the lab, and we will use machine learning algorithm in order to project the model and generalize the motion. And so this is a bit technical, but I will give you the outline and the basic idea. So again, so we will take benefit of the fact that we have a 3D model learned in the lab about the climber, and so we will do a projection of this 3D model onto the real world and until convergence of this alignment. So the motion will obviously be a little bit different. So this is what the machine learning algorithm is made for, is to generalize the motions that we learn in the lab to the real world situation. And so it's kind of reverse the idea of 3D analysis by projection, but at the end it produces 3D analysis by projecting the model. So I won't go into details. I will just the mathematical detail of the machine learning algorithm, but I just wanted to answer one of the questions actually one of your questions about so because it's related about the fact that the human body got a lot of degrees of freedom. It's true. So Frank talked about a couple of hundreds of degrees of freedom, but actually when you perform an action, you use very little degrees of freedom. You're not exploring all your degrees of freedom. When I'm walking, I just do that. When I'm climbing, I just do that. So it's a very reduced set of dimensions. And so this is what is actually typically used in machine learning. So this formal space, so we call it manifold. So we call it manifold of motion, where you embed something with a lot of degrees of freedom, so such like all the degrees of freedom of the body, but you embed that into a manifold of reduced dimension, and the reduced dimension is the fact that you walk, you don't do stupid things with your, you don't do everything with your body, or you climb, and you have some. And so when you were mentioning catalog of motions, this is exactly what we explored actually mathematically with this kind of work. So again, I won't go exactly into details about the equation, but what is important to remember is with the machine learning approach is we learn the 3D shape and motion model in the lab, and then we track motion in the real world by projection and automatic generalization of the 3D model. So here I give you an example, and we'll see the 4th step. So this is a real life, so what we just see is a real life situation with 4 cameras. So here you got steps of the convergence of the model learned in the lab onto the real data, and at the end you will see overlay of the tracking results onto real world video. So this is a result that we obtained for walking, and so this is what is shown here. And so you see the end result. So here, it's a lab, but it's a real world situation like the 2 drones, because we only use 4 cameras and not 68. So where we are now for perspective for climbing. So we've done actually the learning of an accurate biomechanical subject-specific 3D model, and so now we are in the process of implementing those tracking that we successfully applied for walking to climbing, and so this is where we are in the project. So as a conclusion perspective, so we've seen that drones, so this technique of drones can provide support to 3D motion analysis in speed climbing. We've seen that we can already get some interesting, so with the velocity profile, so we can get interesting 3D motion cues to improve performance. We've also seen that it's interesting to work with 3D meshes because it provides more information on dynamics, so to get the real position of the center of mass using the 3D mesh. And just the take-home message for this presentation, so the idea is that in lab research, so in terms of the model, can be leveraged to address real-world situations, so the climbing situation that we face by filming with a drone, And with this approach of using 3D models and machine learning algorithms. So this concludes my talks, and I would like to thank all the participants, all my colleagues for this cool project, and our laboratories, the funding agency, and infrastructures at Boiron, TSF and Boiron. And thank you for the attention. This, so for those who are interested, so there is I made a video of this presentation, and you can ask me, and point you where you can download the video. Thank you for your attention.